Hey guys, I hope you're safe at home and taking enough precautions to not be affected by the coronavirus. I'm back with another video. We are taking a small detour from the typical operating system series that was going on the channel. The reason for that being I had a couple of videos planned out which required a whiteboard, and I do not really have that set up at home. So let's just manage with what I have at home. And the video for today is going to be on load balancing. So this is a very important concept when it comes to distributed systems. Any distributed system which has a client server architecture is something that you always think of a load balancer. You start designing your systems considering you have a load balancer, because the clients cannot really talk to multiple servers at the same time, right? So this is a very interesting concept, and we're going to explore various algorithms which are present for your load balancing. So without wasting any more time, let's get started. Okay, so the most primary thing, what is load balancing and why is it really important? Okay, so let us look at a typical architecture wherein there is a client and there is a server which consists of a web application, and the client is just trying to access the web application. There are a series of HTTP or HTTPS requests and responses which are exchanged between the client and the server. Okay, so now let's start assuming that your website is kind of getting popular. Okay, you've built one of these corona tracking websites and it's kind of catching a lot of traffic now. A lot of clients have started accessing it. So you get a lot of requests, right? And your server is expected to, process the request and send out a response to the clients. So when this happens and the number of clients increases, what is going to happen is at some point your web server is it's not going to accept requests anymore, or even if it's accepting requests, it's going to delay the responses by a long time, and all of these complications start to arise. So this is exactly why you need a load balancer. I know this is more like a weighing scale, but this just demonstrates a load balancer right here. And this can be anything. This can be a hardware load balancer, it can just be a software load balancer which balances on application level. All of that is a talk for another day. What we're going to discuss today is the algorithms that can be applied at this position, and how does it actually apply to the way you send a request and how you get a response back. Okay, this is what we're going to focus on today. So I think you know the reason for having a load balancer. You do not really want each client to send individual requests to each of these servers, and let's say if it fails at some point, then it retries with some other servers and all of that. It kind of complicates it. So the best way to do that is to have a common point of reference wherein the clients talk to the load balancer and the servers as well talk to the load balancer. Okay, so that's the main agenda of having a load balancer here. What are we looking at? We are trying to reduce the client latencies to as minimum as possible. So if you notice in this slide, these are clients. They want your website to load as soon as possible. They want your website's experience to be as seamless, right? So when you want all of that, the load balancer we are trying to put in the middle shouldn't really, extend the latency or increase the latency of these requests. Latency here just means the amount of time it takes for your client to send out a request and the time it takes to get a response back, the difference between the response time and the request when it sends out, right? That is what is called as latency. You want to reduce that as much as possible so that the client has a very good experience with your website. The other point we're also trying to look at is, we being the owners of this website, we are trying to distribute the load on these servers which are present on the right side as equally as possible. We do not want it to be skewed, right? We do not want one server to be serving like 80% of the traffic and the other to just serving like 10%. That's not what we ideally want. So the point to note here is, it's not the number of requests. I'm not talking about the first server serving 100 requests and the second and the third serving only 20 requests. What I actually mean here is how much of the processor and the memory and the disk utilization is happening on each of these servers. Okay, that has to kind of grow uniformly. That's what would make some sense when you're distributing your system. Let's move on to a couple of load balancing algorithms. Let's see the merits and the demerits of each of them. Let's see how well it scales and all of that. So the first thing, of course, which comes to your mind naturally is choosing a random server, right? So you have a load balancer, you get a random request from a client, and you randomly serve it to any of the web servers. You can send the first request to the first server, the first request to the third server. This is just randomly picking servers. Okay, so I'm just trying to denote it with different colors here. The orange packet is going to the third server, the blue is going to the first, and the yellow is going to the second server here. Okay, this is a very randomly chosen algorithm, chosen server by the way. So what happens here? The point that you will have to think about is there something really called as truly random? So can you really randomly distribute load? Okay, like let's say you're getting 20 packets, it doesn't really mean that you're equally distributing it among all the three servers, right? So the number of requests are not getting distributed equally. But as you remember from the agenda of this talk, it's not the number of requests, but the load of these servers that you should consider. The next thing is, it's very simple to implement it when you scale up, okay? At some point, this load balancer is going to become a single point of failure. So you will have to scale this. You're going to have multiple load balancers, which are, serving requests, and they are moving it or redirecting it to any of these servers behind it, right? So when you scale this load balancer, what essentially happens is when you've chosen a random algorithm, it doesn't really affect this. It's still randomly going to pick a destination web server and it's going to send out a request. So it scales really well. This model is very good for scaling. The next thing is, as I said, the latency is not being accounted for. What we're looking at is the request, right? One request comes, you randomly allocate it to any of the servers, but you're not really focused on how long is it actually taking for the web server to process it. Is the web server under high load already? Do you want to send the request to that server again? Right, so these are the things that we're not looking at exactly. So the latency is not at all being considered here. Again, on the same line, if you look at it this way, servers which are underperforming can have more requests being sent to them. Since it is random, you have no control over how many packets or how many requests are being routed to a particular server. Okay, you just assume that not all requests go to one server, but it is totally possible for that to happen as well. Let's assume the second server is underperforming, or its processing speeds have decreased, or whatever. In that case, the load balancer should start sending lesser number of requests to the second server, but it doesn't happen that way. Since it's a random algorithm, it picks up any server. Okay, there's nothing called as truly random, and that's there's a small piece of comic here as well. Okay, so the next algorithm that we're looking at here is called round robin. Okay, as the name suggests, the first request which comes goes to the first server. Okay, what happens to the second request? It should go to the second server. Okay, and similarly you have the third request which goes to the third server. Okay, similarly what is going to happen when there is a fourth request is it will come to the first, and the fifth will go to second, and the sixth will go to the third. So this loop keeps continuing as long as you have requests coming from clients. You might not see your client here because I didn't want to overcomplicate the diagram, but what this essentially means is the servers are going to serve equal number of requests. The first server is always going to serve the number of requests divided by 3 because we have 3 servers. The second similarly is going to serve more or less the same number of requests as long as it's divisible by 3. Otherwise 1 or 2 servers will have like 1 or 2 extra requests. But that's all about it. The problem with this is, you again have the latency problem. You have kind of distributed the packets to the servers, but you still haven't distributed the amount of time it takes to compute or how much of a load is present on each server. You're not considering any of that point. Okay, so let's look at some of the points here. So it does guarantee the same number of requests to all the servers, okay, or at least a similar number of requests if it's not to be equal. Then again, the latency problem that we saw, this does not scale well for scaling your load balancers. Let's say you have multiple load balancers. Let's say you have 3 load balancers here and like 10 servers or something. you need to tell each load balancer where to start from, right? Everything cannot start from the first server. Otherwise, what is going to happen is if you have 10 load balancers, the first 10 requests are going to come to the first server and the other two servers are just going to sit there idle, even though there are more requests to be processed, right? So in that case, you're going to use something like n+1 and you're going to statically hard code it in each of the load balancer. You're going to tell that the first load balancer will start from the first server, the second load balancer will start from the second server, and hope that the clients connect each load balancer in an incremental way. Okay, so this doesn't really scale well when you want to increase the number of load balancers, but you can still get around that. Now we are hitting another problem. This is one more problem which I hadn't discussed in the previous algorithm, in the random algorithm, but it applies there as well. It is highly unlikely for you to keep adding servers with the same hardware configs, right? It might be possible that today you have a server with a particular hardware config, tomorrow you decide to increase the hardware configs of your server and you put these two servers with a higher hardware config. That means they're going to be able to process higher amounts of load. They're going to be able to process more requests, or however you want to take it. So that means it's going to we should have some way to tell the load balancer to start sending more requests to these servers. Okay, that is not really possible in round robin, since you cannot have that logic implemented in this. It's just going to go in a cyclic order, and that's not really a possibility here. So the next thing you're going to look at is called weighted round robin. Okay, how does this work? You have the first request which goes to the first server, second request which goes to the second server, and the third request which goes to the third server. But in addition, you have another logic here wherein you're assigning weights to each of these servers. You should pre-decide the weights that you want each of the servers to carry. So let's assume the first server has got a lesser hardware config, or let's assume it's kind of slow, it's got a different processor, or it has lesser RAM or whatever. So I'm going to give it a weight of 1. Similarly, the second and third, I'm going to give it a weight of 2 and 3. This basically means if I have 3 requests, it's going to uniformly distribute it to all the 3 servers. But any request after that is going to maintain this ratio. This, again, in simple words, after the third request, the fourth request is going to come to the second server, because all the 3 servers have 1 request each. It has 1, 2 and 3. The fourth request can go to either the second server or the third server. Okay, but since both of them have one request in their active queue, we basically start applying round robin to this again. Okay, this basically means the fourth request will start coming from top to bottom. Okay, the fourth request is coming to the second server and the fifth request goes to the third server. Now you have 1 request on the first server, 2 requests on the second server, and 2 requests on the third server. Where should the 6th request go? Since the weight is 3 for this and none of the others have a weight of 3, it's obvious that the request which comes in the 6th place is going to go to the third server. Okay, now that we have satisfied this condition of having 1, 2 and 3 requests, it's again going to start from the beginning. Okay, any request which comes after the 6th request, which is the 7th request, is naturally going to be routed to the first server. Okay, in this way you're going to assign weights to different servers, and based on that you have packets reaching that server, the number of packets which reach that server. So in this case, you can decide the ratio based on hardware configs. You can monitor the performance of each of these servers, and then based on that you can give these ratios. It depends on how you want to take it forward. The second point is, you can also introduce some other service which dynamically checks for latency on each of these servers and then updates these ratios manually. Okay, this is again an addition to the logic which we already have, and it might complicate it in certain scenarios, but this is a choice that you have. So the last point that we talk about here is the weights are present on all the load balancers and not the servers. Okay, the weights that I have mentioned here has to be present on the load balancer and not on the servers. So that's how the load balancer decides which request has to be sent to which server. Okay, so now the typical case where the load balancers are scaled. We have multiple load balancers serving traffic to multiple clients and have multiple web servers behind them. In this case, you need to have these weights present in each of the load balancer. It's not a difficult problem to solve, but you still need to have these load balancers in sync. Otherwise, it is kind of going to get confusing as to which server has to serve what kind of ratio. So the next algorithm that we're going to look at is called least connections. And this is quite a famous algorithm which people use. So what happens here? You have the first 3 requests served to 3 servers, and then you start looking at the number of active requests in each of the servers, okay? And based on that, you start sending out the next request. So if you noticed, the first request had been served by the first server. Since it had processed it fast, the 4th request came here, okay? So you had 1, 2, 3 requests go to the first 3 servers. The first request was the first thing to be processed amongst the 3 servers, and that's the reason the 4th request, when it came to the load balancer, it went ahead and checked which of the servers have the least number of requests in the queue, okay? And it noticed that the first server had 0 requests pending in the queue, and that's the reason it sent out the 4th request to the first server. Similarly, by the time this had finished, the 3rd request was finished processed, which it was completely processed by the 3rd server, and that's the reason the 5th request came to the 3rd server and not the 2nd server. It already had one request, and even the first server had 1 request. So then after that, you notice that the 6th and the 7th request go to the 1st and the 2nd server, because all the 3 had 1 request in their queue. So again, you start following a round robin order or any algorithm that you want to apply when all the queues are equally filled. Let's look at this once more. So the first request goes here, 2nd here, and the 3rd here. First one gets processed, 4th one goes here, 5th one comes here because 3rd was already processed, then 6 and 7. This was a little fast, but I think you can slow down the video and watch it again. Let's discuss a little about least connections algorithm. It's also called as join shortest queue, which means the request which arrives at the load balancer is going to join the shortest queue which belongs to any of the web servers. Okay. Now, if you notice, it routes the request considering the load on each server. This is exactly what our agenda was. Okay, if the load on any of the servers is high, it means that the processing time of each of the requests is high, which means a lot more requests are going to stay in the queue for longer as compared to other servers. This basically means that the other servers are processing requests much faster, the load on that is much lesser, and it is ready to accept new requests. Okay, this totally aligns with one of our agenda of having having load balancing based on how much of load is present on each of the servers already. The second point is what happens in a distributed setup. Okay, let's assume we have multiple load balancers. In that case, the load balancers should be in sync about the active number of requests in each of the web servers. The load balancers are not going to poll each web server and ask it how many requests you have in your queue. This is something which has to be maintained on the load balancer itself. You're going to maintain the number of active connections which have not yet been responded by the web servers, and this has to be synced among each of the load balancers so that they know which server it has to send the request to. Now this is a very interesting thing. We can actually hit something like a race condition. It's not exactly a race condition, but something like a race condition on all the load balancers. Let's look at it this way. Let's assume each of these intersection has got one load balancer. So we have 3 load balancers and 3 servers. And let's assume the 4th request has come to say load balancer B. Okay. Now what is going to happen is, if we assume that all the 3 servers are free, it is going to naturally send it to the first load balancer. Okay. Now what happens when all the 3 load balancers get a request? What is it going to do then? Is it all going to send it to the first server, or is it going to wait for the 2nd server to first finish and then the first server goes, the first load balancer goes ahead and then the 3rd load balancer? Or what happens when there are like 20-30 load balancers? You're going to have 30 packets or 30 requests routed to one server. This is something like a race condition, wherein one server is going to get bombarded because the load balancers are not syncing up about how to send their packets, or which one is going to go first while sending a packet. Okay, so again, this involves another concept called as distributed consensus, which is a topic for another day. But that's a way wherein you resolve this conflict, and you know which load balancer can send requests to which client, or to which web server. The last algorithm that we talk of today is called least connections with randomness. We're going to introduce randomness into the previous algorithm. And I do not really have a diagram for this because it was kind of complicating my animations and I didn't really have control over how it works and all of that. So let's all sit and imagine how this algorithm works rather than me having a diagram for this. Okay. So each load balancer, by the way, this works only for the setup wherein you have multiple load balancers. It doesn't make sense to have this algorithm implemented in a scenario where you have only one load balancer serving multiple clients and multiple servers. So let's assume we have multiple load balancers. Now, when the load balancer comes across any request from a client, let's assume load balancer A gets a request. What the load balancer is going to do is it's going to add another layer of complexity to this. It's going to choose a number of random servers from a set of web servers that it's serving to. Let's assume there are 100 servers and 10 load balancers. From 100 servers, each load balancer is going to pick 10 servers randomly for every request it receives. Once it has a list of 10 servers, what it's going to do is it's going to apply the least connections algorithm to those 10 servers. It's going to find out which is the server which has the least amount of requests in the queue, awaiting in the queue, and it goes ahead and sends the request to that. In this way, what we're trying to do is we're trying to increase the randomness in which these servers are picked, and we are at least not bombarding one server which has the least connections overall in the 100 servers to serve all the requests which comes to the load balancer. So this is one way which you can use to avoid the situation that you were in previously. So yeah, we are trying to solve the problem of race conditions which we hit while solving using least connections algorithm. This works only in a distributed load balancer setup. The problem here is we are adding one more layer of complexity. So which means that even the time it takes to pick these random servers is going to get added to the latency. If it's fast enough, it's good. If that operation takes more time, then your latency increases because of an algorithm that you've chosen. So since you're adding one more layer of complexity, you're adding one more failure, and you're just complicating your life basically. So the next point is, this is very interesting. What happens when, let's assume you have a number of load balancers, you have 10 load balancers and you have 100 web servers. Okay, the number of random server that each of the load balancer picks is something which is static, right? Let's assume we choose 10 as a number. Each load balancer amongst the 10 load balancers is going to choose 10 random servers at any duration. Now this number is very, it's static and it's kind of hard coded in each of these load balancers. Okay, if we choose a number which is close to the actual number of servers, what happens? Let's assume there are 100 servers again. And let's assume we have given the number of random servers it can choose as 95 or 99. In this case, it's going to be very similar to the previous algorithm, least connections, because you're moving more towards having least number of request queues in your sample set, right? Since you are including more number of servers, it is highly probable that most of the load balancers are going to choose the same set of servers again and again. What happens when you choose the random number to be very less? Like let's say you have 100 web servers serving requests, but on the load balancer you choose the number of random servers it can choose is 5. What is going to happen in this case is it's going to move very close to the random algorithm that we had seen in the first case. It is highly unlikely that all of your sample sets have like very close to the least connections that any of the web servers are serving. So this basically means you're just randomly choosing web servers and you're trying to send requests to it without really accounting for latency here. I really want you to think more about this point. It's very interesting. So these are the only 5 algorithms that I wanted to discuss in today's video. And all of these techniques that we have seen so far assume that the applications are stateless. This basically means that the servers do not really have to serve or store the state of users. Okay, the users can connect to any random server and still get a request responded by it. Okay, we do not store the state of the application that the user is using. The reason we haven't considered that is persistent connections is another problem that we have to look at. So basically, a load balancer, when it receives a request from a client, it's the duty of the load balancer to make sure the client request goes to the same web server again and again. Okay, this is basically adding one more layer of complexity to it, and I would rather solve this problem separately in another video. I have a few further readings that you can do. So there is another algorithm called join idle queue, wherein the client or the web server basically reports to the load balancer, telling that, okay, this is my current performance. I can serve more requests. Please send across more requests to me. Okay, this is one other way wherein load balancers get real-time insights by the web servers, and based on that, it decides which web server to send a request to. The other thing is, this is more to do with the persistent connections, which I can cover in another video. Sorry. So what happens is, this algorithm is called source IP hash algorithm, and you can kind of include another concept called consistent hashing into this, so that you basically know which client is being served to which web server. Okay, and the load balancer remembers that, and based on a hashing principle, it is basically able to serve the request to the same web server again and again. The last algorithm that you can also look at is called global server load balancing, and most of the big companies these days use this algorithm. This is because they have their applications spread across the globe. They have applications running in different data centers, and for a load balancer to be able to serve a request, what it has to also calculate is it has to account for your geographic location, the latency that the client can observe based on which data center it routes your traffic to, and various other scenarios. So I have a very good paper linked to this as well, and you should definitely go check this out. Okay, so I have a couple of references as well for this video. The second point here, this is a video by Tyler McMullen, and he talks about why load balancing is very close to impossible. Okay, this is a very interesting talk. If you really like mathematics and you like looking at graphs and all these probability and all of that, you should really go ahead and watch this video by him. It's really interesting. So that is all I had for this video. I hope you liked the video and you've taken back something from the video. I hope you try out these algorithms and you come up with which algorithm to choose in specific scenarios of your applications. If you did like the video, please share the video with your friends as well, so that they benefit from the content. And please do consider subscribing to the channel if you haven't done so. Thank you, and see you all in the next video.